So once again, welcome everyone to this latest edition of the seminar on precision physics and fundamental symmetries. It's my great pleasure to welcome Yevgeny Stadnik to give a talk here today. Yevgeny is currently an assistant professor at the Kavli Institute for Physics and Mathematics at the University of Tokyo. He graduated from the University of New South Wales, Australia, supervised by Victor Flambaum. And after this, he moved to the University of Mainz in Germany as a Humboldt Fellow, working in the group of Dima Budka. Very recently, Yevgeny has become a member of the advisory board of the Virtual Institute of Feebly Interacting Particles, which is an initiative jointly between Fermilab and CERN. Yevgeny is very well known for his groundbreaking work on detecting axions and axion-like particles using precision experiments at low energy, and for investigating the variation of fundamental constants. We're really excited to hear him talk today on searches for dark matter and topological defects with atoms and photons varying fundamental constants. Just a reminder for those who are new to this seminar, we'd ask you to post your questions in the Q&A window. And usually for this seminar, we'll have a little pause halfway through. And if anyone has any questions for the first half of the talk, please post them straight away. And Yevgeny will deal with them at the appropriate point, roughly at the halfway mark, so that we break up the talk a little bit. And then we'll have a further Q&A session at the end for any remaining questions. So please, if you have the question, post them in the Q&A. We'll deal with some of them halfway through and then the remainder at the end. So with that, I'd like to hand over the floor to Yevgeny. Thanks very much for agreeing to give this talk, and we're very excited to hear what you have to say. Thank you very much.
So thank you very much for the introduction, and thank you very much for the invitation to present the seminar to you today. The topic of my talk today is how we can look for dark matter and topological defects by using experiments from the fields of atomic and optical physics. And today I would like to specifically focus on the possibility of looking for effects where the fundamental constants of nature may vary in time and in space. So in the first half of the talk, I would like to focus on the topic of dark matter. And here there are a number of independent astrophysical observations which collectively tell us that there is about 5 times more dark matter in the universe than the ordinary visible matter that we see around us. So the majority of the dark matter is confined to the galaxies, where it forms these spheroidal dark matter halos. Now, from the point of view of direct detection experiments in the laboratory, there are 2 important features of the dark matter in the vicinity of the solar system. So the first is that we understand that the average energy density of the dark matter is given by about half a proton rest mass per cubic centimeter. And we understand that this is an extremely small density compared with the usual matter-based densities that we see in terrestrial environments. And this is also comparable to some of the best vacuum systems that we can produce in the laboratory on Earth. So this is an extremely small density. The second important feature of the dark matter near the Sun is that the root mean square speed of the dark matter is estimated to be about 300 kilometers a second. And this number comes about from the requirement that the dark matter should neither escape from the gravitation well of the galaxy and nor should the dark matter collapse to the center of the galaxy on a cosmologically large timescale. So 300 kilometers a second is about 1,000 times slower than the speed of light. So this means that the galactic dark matter is a non-relativistic form of matter. And the dilute and non-relativistic nature of matter, dark matter, both turn out to have important implications for how we try to devise experiments to try to find and identify the dark matter. So over the past several decades, most of the experimental efforts in terms of direct searches for dark matter have tried to focus and look for so-called weakly interacting massive particles, or WIMPs for short. And in this case, their canonical masses range from about the mass of a proton up to about 1,000 times the proton rest mass, or about 10 times the Higgs boson. However, in the absence of any strong experimental evidence in favor of WIMPs, Over the past decade or so, there's been growing interest in terms of searching for alternatives to these WIMP particles. And one of the interesting possibilities which has attracted significant attention is the possibility that the dark matter may consist of bosonic particles with extremely small masses. And these types of bosons are expected to live somewhere in this green region over here. And so what we see is that because this range of masses is complementary to the usual masses of WIMPs, having very different ranges of masses means that we'll have to use conceptually very different types of techniques in terms of performing the different types of searches. And we will see how this is achieved very shortly. So in this talk, I'd like to focus on the simplest types of bosons, which are spinless particles, where the field has a single degree of freedom. And if these low-mass spinless particles were produced in the early universe, then they could subsequently form a coherently oscillating classical field phi. So this field is basically characterized by two parameters. One of the parameters is the angular frequency of the oscillations, and this is governed by the mass of the dark matter particle. And the second parameter here is the amplitude of the oscillations phi 0, and these oscillations take place about the minimum of a quadratic or harmonic potential. So as a result of these oscillations, there is a non-zero energy density, which is associated with this dark matter field. And the time average energy density is a function of the frequency and the amplitude of these oscillations. And the dependence on these two parameters is precisely what we have in the case of the usual underdamped harmonic oscillator. So the reason why the oscillations of this dark matter field are coherent is that the dark matter particles that we deal with are non-relativistic or cold. So in other words, these dark matter particles carry very small kinetic energies. And so the overall energies of the dark matter particles are all going to be very similar, and they'll be given approximately by the rest mass energy of the dark matter particle. However, the oscillations of the dark matter field are not perfectly coherent. In a local galactic region where the root mean square speed of the dark matter is expected to be about 300 kilometers a second, the spread in kinetic energies carried by the dark matter particles would be expected to be at the level of 1 part per million relative to the rest mass energy of the dark matter particle. And so what this implies is that there should be a finite coherence time associated with the oscillations of this dark matter field, and the coherence time should be given by about median periods of oscillation. So for all intents and purposes, we can treat the oscillations of the dark matter field as being practically monochromatic, and the quality factor which is associated with the oscillations is going to be about 1 million, which is comparable to a very good resonator in the laboratory. So what we basically expect to see is if we perform measurements on a timescale which is much less than the coherence time, then in that case, the amplitude of the oscillations would be expected to remain approximately constant over time. However, if we continue to perform measurements on a timescale which becomes comparable to or greater than the coherence time of the field, then in that case, the amplitude of the oscillations would be expected to fluctuate over time in some stochastic manner. And in the simplest case, the underlying probability distribution function, which governs these stochastic fluctuations, is essentially given by a Rayleigh type distribution, shown by the curve in red here. And this can be understood by the simple analogy of the chaotic Gaussian light source. Now, on the other hand, in order to have a classical field, we need to have a sufficiently large number of these dark matter particles within a single de Broglie volume. And for the local galactic dark matter density, we can satisfy this classicality requirement, provided that the dark matter particle mass is less than about 1 electron volt. So in this case, we have to have extremely low mass particles, which are at least 1 million times lighter than the electron. And for this particular type of dark matter, we are especially interested in this mass range from about 10 to the minus 21 electron volts. going all the way up to about 1 electron volt. So this upper mass bound, this upper mass cutoff of 1 electron volt is just a requirement of classicality. If the dark matter field was not necessarily classical, then in principle the dark matter particle mass could be much larger than 1 electron volt. On the other hand, if these low mass dark matter particles are to saturate the observed dark matter abundance, then the particle mass should not be less than about 10 to minus 21 electron volts. And the simplest way to understand this bound, or the most robust way to understand this bound, is that these low mass dark matter fields are expected to suppress the formation of structures on length scales below about the wavelength of the dark matter field. So this is a consequence of the wave uncertainty principle. And if we look at the structures that we see in Lyman upper forest measurements, these measurements rule out dark matter particle masses less than about 10 to minus 21 electron volts. There's also a similar figure of merit for this low mass bound, which comes from the simple argument that the dark matter Broglie wavelength should fit inside the halo sizes of the smallest dwarf galaxies, and this gives us a very similar low mass bound in this case. So what we see is that there's a very broad range of possible dark matter particle masses, which spans about 20 orders of magnitude. And this means that we can have a similarly broad range of possible frequencies of oscillation, which again span about 20 orders of magnitude. So on the lower end of the frequency range, the frequency is about 100 nanohertz, which serendipitously corresponds to a period of oscillation of the order of a month. On the upper end of the frequency range, we have about 100 terahertz frequencies, which corresponds to the infrared region of the electromagnetic spectrum. So even though this is a very, very broad range of possible frequencies, the fact that these frequencies lie in very physically accessible and understandable ranges, it means that we can actually try to devise experiments which cover large regions of this frequency parameter space and potentially the entirety of the space. Now, the way that we can actually look for these low mass dark matter fields is going to be very different from traditional WIMP searches. And that is, in the usual searches for WIMPs, we generally look for particle-like signatures. For example, we can have a flux or WIMP particles coming in and scattering off atomic nuclei. And as the WIMP particles scatter onto the nuclei, they will deposit a certain amount of energy onto the nucleus and cause a recoil. However, these low mass dark matter particles are not only low mass, but they are also non-relativistic. So this means that the typical kinetic energies that these dark matter particles carry are going to be many orders of magnitude below the energy thresholds in these traditional WIMP detection experiments. So in other words, it's practically impossible to look for the particle-like signatures of these low mass dark matter fields. But what we can do instead is actually take advantage of the fact that there will be a very large number of these low mass dark matter particles. And when we have very high occupation numbers, we can expect to see certain field-like behavior emerging in which numerous dark matter particles act collectively. And as a result of these collective effects, we can expect to see certain wave-like signatures, perhaps. So the exact types of wave-like signatures that we can look for will depend, of course, on the type of dark matter particle that we have. And also they will depend on how this dark matter field interacts non-gravitationally with the ordinary matter. So there are a number of possibilities for how this can happen. In this talk, I'll focus on only one broad possibility, which is that the dark matter may induce apparent variations in the fundamental constants. So the simplest model which admits these variations of the physical constants essentially involves the interaction of an oscillating scalar field phi with the electromagnetic field tensor F. And so as a result of this interaction, we would expect there to be apparent oscillations in the value of the electromagnetic fine structure constant alpha. So this is the parameter which governs the strength of the electromagnetic interactions in the standard model. And the oscillations in the value of alpha will take place at a frequency which is governed by the mass of the dark matter particle. Also, we see here that in the denominator, we have this parameter lambda, which appears in the interaction. And lambda is a parameter with dimensions of energy. And basically, the higher the energy scale, the feebler the interaction in this case. So for gravity, lambda would be given by the Planck scale, which is 10 to the 19 giga-electron volts. Okay, this oscillating scalar field phi may also interact with the fermion fields. And in this case, we would expect it to be similar apparent oscillations in the values of the fermion masses. And in this case, the lambda parameter would generally be expected to be different and possibly unrelated to the lambda parameter in the electromagnetic interaction above. Another interesting point to take into consideration is that the galactic dark matter halo is understood to be essentially at rest in the galactic frame of reference, whereas the ordinary matter, which includes the stars and the solar system, are observed to be orbiting about the galactic center. So what this means is that in the laboratory frame of reference, the expression for the oscillating scalar field phi here would also contain this additional motional gradient term in red as a sort of standing wave expression. And in the presence of this motional gradient term, if we have these linear and phi interactions, then we would expect forces to be exerted on test particles in the laboratory frame of reference. So these forces would be, first of all, oscillating in time, and also they would be directed along the relative motion of the apparatus or the test particle through the dark matter halo. Now, because these linear phi interactions are non-universal, meaning that they do not couple to the total mass of a test body, but only to some component of the test mass, these types of forces are generally expected to violate the equivalence principle in this case. So apart from these linear phi interactions, we can also have analogous quadratic and phi interactions with the standard model fields. And in this case, these phi squared interactions would again exhibit the same types of oscillating type signatures like the ones that we saw above here. However, in the case of phi squared interactions, the phenomenology is significantly richer. In particular, with phi squared interactions, we would expect there to be changes in the fundamental constants of nature, which are correlated with changes or differences in the dark matter density. And this type of effect can arise most simply due to the expansion of the universe and the associated dilution of the dark matter density over time. In addition to this, we also understand that in terrestrial experiments where we're in the vicinity of a massive body like Earth or the Sun, we expect there to be gradients in the dark matter density developed in the vicinity of these massive bodies. And so in this case, in the presence of these phi squared interactions, we would expect there to be additional equivalence principle violating forces directed along these dark matter density gradients. There is another important difference between linear and quadratic interactions, which manifests itself in the vicinity of massive bodies, such as Earth. So let's have a look at the linear and phi interactions firstly. In this case, the classical equation of motion for the scalar field phi here is the usual Klein-Gordon equation with the source term in pink provided by the linear phi interaction here. So if we look at the scalar field profile outside of a massive spherical body, then we see that it consists of, firstly, the oscillating term on the left here. So this corresponds to the oscillating dark matter component. And then there's also a second term on the right here in pink. And this is a Yukawa type term, which arises due to the exchange of a scalar boson between a source body and the test body. So this is a relatively well-known linear superposition. What is perhaps a little less well-known is what happens in the case of the quadratic and phi interactions. So here we see that because of the difference in the structure of the two operators, in the case of the phi squared interaction, we no longer have the source term in pink in the classical equation of motion for the scalar field phi, but we instead have this effective mass term in orange. And the role of this effective mass term is that if we're performing experiments where there is a non-zero density of ordinary matter, the effective mass of the scalar particle is no longer simply given by the bare mass of the particle, but the effective mass is now going to be shifted away by an amount which is determined by the strength of the non-gravitational interaction, and also it'll be determined by the local matter-based density. If we now look at the scalar field profile outside of a massive spherical body, we see that it again consists of this oscillating term on the left. So this corresponds to the oscillating dark matter component, just like on the left-hand side. However, now the amplitude of the oscillations is no longer simply phi0, but the amplitude will be modified by some factor, which depends on how far away from the center of this massive body we find ourselves. So in other words, there are, in this case, explicit gradients in the density of the dark matter field developed around a massive body. And depending on the sign of the phi-squared interactions that we start with, we can in principle have either amplification or screening of the dark matter density when we're close to the surface of this massive body. So although we don't have the simple exchange of a single boson between two test bodies in the case of phi-squared interactions, what we do have is the possible simultaneous exchange of two scalar particles between two bodies. And this type of exchange corresponds to a quantum force because there is one loop in the process here. And in this case, the expression for the scalar field outside of a massive spherical body will contain this extra quantum correction, which explicitly depends on the Planck constant. And now we have this modified Yukawa type term, which falls off with a distance like 1 on the distance to the third power here. This type of quantum correction is, generally speaking, much less efficient and induces observable signatures than the usual Yukawa type term on the left-hand side in pink. As I mentioned in the previous slide, as a result of the expected motion of the apparatus or test particles through the dark matter halo, we expect it to be motional gradients observed in a laboratory frame of reference. And so what we basically see in this case is that already in the simplest models of scalar dark matter fields with either a linear or quadratic interaction, there are numerous types of gradients which are present in these expressions. So these gradient terms are expected to induce equivalence principle violating forces, which we can search for with so-called fifth force experiments. So traditionally, tests of the weak equivalence principle on macroscopic scales have tended to be done most precisely by using torsion pendulum experiments or torsion balances. However, in recent years, atom interferometry techniques have also started to emerge as powerful probes of the weak equivalence principle. So the improvement with these types of experiments has been by about 5 orders of magnitude over the space of the past decade or so. And now the sensitivity of atom interferometry experiments is in fact starting to approach the sensitivity of the more traditional torsion pendulum experiments. Well, now let's take a look at how we can look for these oscillations in the physical constants due to the dark matter field. So in this talk, I'll basically start with the lowest frequencies of oscillation that we can search for, and then I'll talk about the methods for the higher frequencies later on. At the lowest frequencies, one of the most powerful methods we can use involves atomic spectroscopy searches. So the basic idea here is actually in some ways not new because atomic spectroscopy and clock-based techniques have been used for a number of decades now to look for possible slow changes in the fundamental constants. The basic idea is that if we have two atomic transitions between two different pairs of atomic energy levels, then if we measure the ratio of these two transition frequencies, if one or more of the fundamental constants of nature were to change over time, then in this case we would expect the ratio of the two frequencies to also slowly drift over time. And this is provided that the two transitions have different sensitivities or responses to changes in the fundamental constants of nature. These sensitivity coefficients Kx are not measurable experimentally, but they are calculable using numerical atomic calculations. And the sensitivity coefficients, which are used for a variety of experiments, practically all of the existing clocks and many of the clocks under development, have actually been calculated for us, courtesy of the work of Professor Victor Plumbaum and co-workers in Sydney over the past 20 years or so. Just to explain where these sensitivity coefficients come from and how they arise, let's take a look at a typical or archetypal atomic optical transition. In this case, the transition frequency scales proportionally to the non-relativistic atomic unit of frequency in red. So this is basically the Rydberg constant. But then this non-relativistic factor is also multiplied by the relativistic factor in blue. And this relativistic factor depends on the nuclear charge of the atom and also in the fine structure constant alpha. So if we measure the ratio of two different atomic optical transition frequencies, in this case, the non-relativistic unit of frequency is common in the numerator and denominator, which means that this unit cancels in the comparison. And so what we're left with is simply the ratio of the two relativistic factors in this case. The relativistic factors in these atomic transition frequencies generally tend to grow as we move towards heavier atoms where the nucleus has a larger charge. And the reason for this is that when the electrons are orbiting close to the nucleus, their momentum and their velocity increases with the nuclear charge. So we see that going from the strontium clock through to terbium and into mercury, there is a regular enhancement in terms of the sensitivity to alpha variations in this case. Apart from optical transitions, there are also atomic hyperfine transitions, which are used as the basis for microwave clocks. In this case, the archetypal microwave transition has a different dependence on the finite constants. So first of all, we see that there's an extra power of alpha squared here, which arises due to the short-range nature of the magnetic hyperfine interaction between the atomic electrons and the nucleus. And this factor of alpha squared gives rise to an extra factor of 2 in the relative sensitivity coefficient to alpha variations for hyperfine transitions. And again, we also see that as we move towards heavier atomic systems, the size of the relativistic correction factor increases, which means that we have greater sensitivity to alpha variation in this case. In the case of hyperfine transitions, there's also sensitivity to variations in the electron to nuclear mass ratio. And because of the appearance of the nuclear magnetic moment here, there is also, generally speaking, some, albeit mild, dependence to variations in the ratio of the light quark masses to the QCD or strong scale. So what we've seen on this slide is how the story works for the sort of regular transitions that we deal with in experiments. However, it is possible to have irregularities and significant enhancements on top of these archetypal sensitivity coefficients. In particular, in a variety of different systems, it's possible for the relative sensitivity coefficients to be greatly enhanced when we deal with transitions between nearly degenerate levels. So for example, in atoms, one example of where this occurs is in the case of atomic dysprosium, where there is a pair of opposite parity levels which are naturally nearly degenerate. So this is an accidental degeneracy. And in this case, we have transitions in the radio frequency range, which is not ideal for metrological applications. However, the relative enhancement factor to alpha variations is nevertheless enhanced by of the order of 1 million to 10 million compared to a typical optical atomic clock. And the precise enhancement factor depends on the type of isotope that we use in the experiment. In the case of highly charged ions, we can have a very interesting situation. So if we look at the isoelectronic sequence for an element such as silver, in this case, we see that the dependence of the ionization energies of the 5s and 4s levels is different depending on the actual number of electrons that we ionize. We see that there would come a point in this particular isoelectronic sequence where the two energy levels would undergo a level crossing, and around this point, it is possible to have a transition between these levels, which is not in the 100 electron volt to kilo electron volt range, which is typical for highly charged ions, but instead the transition may serendipitously happen to lie in the more convenient optical frequency range, which is great for optical metrological purposes. So as an example, in the bismuth isoelectronic sequence, there is the californium 15 plus highly charged ion, and the sensitivity coefficient to variations in alpha is enhanced by about 2 orders of magnitude compared with the typical optical atomic clock. In the case of molecules, the story gets even more interesting because in molecules, there is a much richer energy level structure that we can have. And this arises due to the much richer types of contributions that we can have from different energy levels in molecules. So in molecules, we have the fine structure and hyperfine magnetic contributions, just like we do in atoms. However, there are a couple of contributions which are unique to molecules and do not appear in atoms. In particular, in molecules, we can have the effects of rotational, vibrational, and omega doubling type contributions. So as an example, for a far infrared frequency transition in hafnium fluoride ion, it's possible for the relative sensitivity coefficient to alpha variation to be enhanced by about 3 orders of magnitude relative to a typical optical atomic transition. And also the enhancement factor to electron to nuclear mass variations is by about 2 orders of magnitude compared with a typical microwave atomic transition. Finally, there is, to the best of our knowledge, one very interesting case of enhanced sensitivity coefficients in nuclear transitions. In particular, we understand that there is a low energy isomeric transition between the ground and first excited states of thorium-229. The most recent measurements suggest that the transition energy is about 8 electron volts. And this is quite anomalous because typically in nuclei, we expect nuclear transition energies to be of the order of 100 kilo electron volts, so up to the mega electron volt range. However, in thorium-229, there is a very fortuitous cancellation between the electromagnetic and strong force intervals to give us this rather unique low energy transition in this case. So in this case, this would be an ultraviolet transition, and the sensitivity to alpha variations in this case would be enhanced by about 4 orders of magnitude relative to a typical optical atomic clock. So we can take all of this existing knowledge, which has been used previously in searches for slow variations in the physical constants, and simply apply this to search for slow oscillations of the physical constants. So the basic idea is essentially the same. We still measure the ratio of 2 different atomic transition frequencies, except now what we do is we want to look for oscillations about the mean value of the transition frequency ratio in this case. And the frequency of the signal that we will look for in this case is going to be governed by the mass of the dark matter particle. So this type of approach has been utilized by a number of groups around the world now. And this has been done using about half a dozen different clock-clock combinations. And this has mainly been performed using the highest possible grade transitions transitions and clocks developed in metrological institutes. So if we want to consider faster oscillations of the physical constants, then it becomes possible to actually use a number of conceptually different approaches which haven't traditionally been used in searches for varying fundamental constants. So one of these ideas is based around the use of cavities or solid materials. And we know that in the non-relativistic limit, the length of a solid scales proportionally to the atomic bore radius. So if we have a reference frequency, which is summed by the length of the solid, then provided that changes in the fundamental constants occur at an adiabatic rate, the reference frequency would respond to oscillations in the electron mass and the fine structure constant alpha. So we have to reference the cavity against something else, and the other reference frequency can come from, for example, an atomic transition frequency. So if we have an electronic transition frequency, which is in this case, let's suppose an optical transition frequency, in the non-relativistic limit, the transition frequency scales proportionally to the Rydberg constant, and so we see that there's an extra power of alpha compared with the cavity reference frequency on the left here. If we measure the ratio of the atomic transition frequency to the solid cavity reference frequency, we see that we'd be sensitive to oscillations in the value of defined structure constant alpha in this case. And this type of idea of comparing atomic transition frequencies against cavity frequencies has been utilized by quite a large number of groups around the world now. And this is done using at least half a dozen different clock cavity combinations and with some variations involved. Now, it's not essential to reference a cavity against an atomic transition frequency. We can also reference two different types of cavities. So we can keep our solid cavity on the left here from before, and now reference it against a different type of cavity on the right-hand side. So this second type of cavity on the right can consist of a pair of mirrors, which are freely suspended from double pendular suspension systems, as shown on the right-hand side here. In this case, if the dark matter frequency of oscillation lies above the natural frequencies of these pendular systems, then the length of the second type of cavity will be practically constant in time. So what this basically means is that the second cavity can provide us with an excellent reference frequency, which is practically insensitive to the external dark matter field and its interactions in this case. So in this case, if we reference these two different types of cavity reference frequencies against one another, then we see that we'd be sensitive not only to oscillations in the value of alpha, like we were in the atom to solid cavity comparison from the previous slide, but now we also gain a sensitivity to apparent oscillations in the value of the electron mass here. So in other words, the manner in which we do the comparisons is important in terms of determining which parameters our experiments are going to be sensitive to. And at the moment, there is a small-scale experiment currently being developed precisely to perform these types of cavity-cavity comparisons by a group in the US. So we can take this cavity-based idea and actually apply this to larger-scale instruments. In particular, we can apply this idea to large-scale gravitation wave detectors, which are based on the principle of laser interferometry. And the simplest type of laser interferometer that we can have is a so-called microscope configuration, where the best example is the GX600 detector, which is located just outside of Hanover. And the main idea here is that we have two arms of very similar length, and we basically just want to compare the difference between these two optical path lengths and see the resulting effects by interference at the output port. So as far as the effects of the dark matter on the two arms are concerned, because the arms are basically the same length, the effects of the dark matter are going to be common mode in this case, and those types of effects in the arms will tend to cancel. What doesn't cancel in the actual output port are effects which arise due to the dark matter in terms of how it can interact and affect the geometric asymmetries in the detector. So in the microscope interferometer, the main source of these geometric asymmetries is in the central element, which is the beam splitter here. And in this case, we see that the main reflecting surface of the beam splitter is located on the top left edge over here. This is because the bottom right edge is anti-reflective coded. So the main reflection point in this case is going to be at this point here on the top left. So if the thickness of this beam splitter were to oscillate in time, for example, due to the oscillating dark matter field, then at some moment in time, the main reflecting surface would be shifted towards the top left blue line over here. And so at this moment in time, the main reflection point would now be shifted towards the left here. So if you look at the bigger picture, we see that at this moment in time, the horizontal length of the interferometer will be slightly elongated relative to the length of the vertical arm. And because the interferometer is searching for differences in the, searching for changes in the difference between the two optical path lengths, in this case, we'll be sensitive to oscillations in the thickness of the beam splitter, and we would also be sensitive to oscillations in the refractive index of the beam splitter material. And this type of idea has been actually recently utilized by a number of members of the GX600 collaboration and also by members of the Fermilab bolometer experiment. and the results are reported in these two publications. Now, apart from this simple broadband search, it's also possible to modify these experiments to perform what is known as a resonant narrowband search. The basic idea in the latter case is that when the dark matter frequency of oscillation matches onto the vibrational frequency of the beam splitter, in this case, we can have a sizable enhancement in the dark matter-induced signal due to an increase in the dark matter-induced thickness oscillations of the beam splitter. So the enhancement factor can be as large as about 1 million, because if we recall from earlier, the dark matter oscillations are expected to be practically monochromatic with a quality factor of the order of 1 million. Now, because we don't know what the dark matter particle mass is before we start the search, we have to perform the measurements in such a way as to allow us to scan over a range of possible dark matter particle masses. And one of the simplest ways to do this is by taking the temperature of the system and incrementally varying the temperature. And when we vary the temperature of the system, we know that the thickness of the beam splitter will tend to change, and also more importantly, quite often more importantly, the sound speed in the beam splitter material would also change. So by varying the temperature of the system, it becomes possible to scan over a range of possible dark matter frequencies of oscillation in this case. So what we've just described is what happens for the microscope configuration. The more modern gravitational wave detectors are based on the principle of the Fabry-Perot microscope configuration. And the main difference between the two configurations is that compared with the microscope configuration on the left, the Fabry-Perot microscope configuration has an extra set of mirrors inserted into the two arms here. And these mirrors essentially allow us to amplify the light beam intensity between the ends of the mirrors here to form these Fabry-Perot cavities here. So this light beam enhancement is, so the enhancement in the power in the light beam is advantageous if we look for the usual gravitational wave, because the passing gravitational wave would affect all the space points between these two mirrors. However, as far as the effects of the dark matter, on the beam split is concerned, having a large number of passages of the light beam between the ends of the mirrors here is not necessarily an advantage, because for every few hundred passages of the light beam between the ends of the mirrors of the cavity, there is only one passage through the beam splitter here. So the dark matter-induced effect via the beam splitter, as we see it at the output port, is actually going to be suppressed by a factor of a few hundred in the case of this type of configuration. Now, we can overcome this limitation to essentially a large extent, most simply by changing the thicknesses of a pair of mirrors in one of the two Fabry-Perot cavities here. And so when we do this, we see that the main effect of the dark matter-induced signal is no longer going to manifest itself through the effect of the dark matter on the beam splitter, but now the main signal will arise actually due to oscillations in the mismatch of the arm mirror thicknesses in this case. And it's not necessary to change the thicknesses of the arm mirrors by a grossly large amount. In fact, changing the thicknesses of the mirrors by only 10% between the two arms is already sufficient to give a significant improvement in the sensitivity to the dark matter, whilst also retaining the sensitivity of the detector to the usual gravitational waves. In fact, one of the nice features of both of these types of searches is that we can look for the dark matter field and the usual gravitational waves simultaneously. Okay, so turning now to the results. So here we have some limits on the linear interaction of the scale dark matter field with the electromagnetic field. Now down the bottom left here, we have the clock-clock comparison limits shown in blue. And we also have the clock cavity comparison limits shown in red. So the limits in blue and red both come about from looking for the oscillations in the value of the fine structure constant alpha due to the oscillating dark matter field. So on the x-axis, we have the logarithm of the dark matter particle mass, and larger particle masses go to the right-hand side here. And on the y-axis, we have the logarithm of the interaction parameter, and feeble interactions go down the page in this case. What this means is that the limits in blue and red collectively give us up to a factor of 10,000 improvement over the previous limits shown in green and yellow, which come about from looking for equivalence principle violating forces, which were sought with torsion pendulum experiments. Now, at the higher frequencies of oscillation, specifically the audio frequency band range, in this case, there are limits which have been obtained with some of the data, some of the older data collected by the GS600 detector, and these limits are shown by cyan here. Now, if we could modify, for example, the LIGO experiment in such a way that the arm mirror thicknesses in the two arms would be made different by about 10% between one another, and also if we reach the design sensitivity of advanced LIGO, we estimate that it should be possible to improve the sensitivity down to the dashed blue line in this case. Another interesting point to take into consideration is that there are different types of interactions that these dark matter fields may have. In particular, in the case of the linear interaction of the scalar dark matter field with the electron field, the fifth force bounds in yellow and green are weaker by about a factor of 20. And so in this case, there's actually more available parameter space to probe with these optical interferometry techniques. And for the electron coupling, the GS600 bounds, in fact, already give the most stringent bounds of a relatively narrow region of particle masses. In the case of the quadratic interaction of the scalar dark matter field with the electromagnetic field, the Cox comparison limits are shown down the bottom left here. So these again come about from looking for these oscillations in the value of the fine structure constant alpha due to this oscillating dark matter field. Now here the picture is a little bit different. In fact, if we go to the right here, we see that we have these astrophysical Big Bang nucleosynthesis bounds in red, which essentially come about from looking for these slow drifts in the value of the fine structure constant alpha, which are correlated with changes in the dark matter density as the universe expands. And so here we're basically looking for the effect of these slow changes in alpha on the primordial primordial abundances of light elements. So the limits in blue and red collectively give us up to a 15 orders of magnitude improvement over the previous laboratory bounds from different signatures in purple, and also different types of astrophysical bounds in gray. In the middle of this graph, we see that we have these regions in yellow and green. So these are torsion pendular experimental limits, which come about from looking for rather unusual equivalence principle violating forces. They're unusual in the sense that we don't look for a simple Yukawa type force, but we instead look for an equivalence principle violating force, which is directed along the dark matter density gradient around the Earth. The difference between these two experiments is that the yellow experiment is a laboratory experiment, which is performed close to the surface of Earth, whereas the green measurement here is a space-based experiment. So it's performed at an altitude, it's performed on a satellite at an altitude of about 700 kilometers in this case. And in fact, we see that as we go towards larger dark matter particle masses and strong interaction strength, we actually enter a region of parameter space where the dark matter density becomes strongly screened near Earth's surface, because as I mentioned earlier, in the case of particle interaction, we can actually have the effects of screening emerging in the vicinity of dense bodies. So what this basically means is that if we can position our apparatus relatively far away from Earth's surface, then we can gain a huge advantage compared with analogous experiments performed close to the surface of Earth. So that's all I would like to say in the first half of the talk, and I'm happy to answer any questions before continuing to the second half.
Just to give people a chance, if they want to write any questions, I can jump in with a quick one. What makes a good molecule for having an enhanced sensitivity coefficient? Is it basically the same as what you look for an electron-electric dipole moment search, or are there any extra considerations?
It's a little bit different. So let's go back. In electron EDM searches, the main consideration is generally having a very high nuclear charge, because the size of the electron EDM effect generally grows as a nuclear charge to roughly the third power. And also we, in molecules for EDM searches, we like to have a large effective electric field inside the molecule. So we want to have essentially a pair of transitions which can be very easily mixed in the presence of a very weak external applied electric field. So we want to have a very good high polarizability. In this case, the picture is a little bit different. So with molecules, in terms of searching for variations of physical constants, it's not essential to have the heaviest molecules. So for example, something like the fine structure and hyperfine magnetic energy intervals, these types of relativistic corrections would tend to grow with the size of the nuclear charge. However, the rotational and vibrational energy intervals, generally speaking, wouldn't gain this type of advantage. So if we could, for example, have a nearly degenerate transition between levels where there was, for example, an accidental cancellation between the rotational, vibrational, or even the omega doubling intervals, then in principle we could have a very sizable enhancement factor in that case. But in terms of searches for variations in the fundamental constants, it's not necessary to have very heavy species present in the molecules. And in fact, we can already have quite some interesting enhancement factors if we're dealing with purely diatomic species. Polyatomic molecules, of course, have even more degrees of freedom, and they're even a simple molecule like ammonia, where nitrogen has a relatively low nuclear charge. In that case, we can still gain a sizable enhancement factor, for example, to electron to nuclear mass variations, even though we're dealing with a relatively light molecule.
Thanks, that was really great. I don't see any other questions at this time, so but of course people can keep posting them at the end of the talk and we can come back to them. So I think go ahead. Thanks very much.
Thank you. So that means it must have been a very clear talk so far. Okay. So now in the remaining part of the talk, I'd like to switch topics and discuss a somewhat related topic of how we can look for possible macroscopic dark objects. And the basic idea here is essentially, well, I guess coming from recent interest by a number of experimental groups in atomic physics to look for the possible transient signatures of these types of objects if they were to pass through the Earth. The basic idea is that if we can use a strategic global network of detectors, it may be possible to look for the correlated in time signatures of these passing objects. So in some ways, this is quite similar to traditional searches for gravitation wave detectors using a global network of laser interferometers, except the difference between the two types of searches is that a gravitational wave is understood to be massless, and so it propagates at the speed of light, whereas one of these dark objects are expected to be massive. And so what this means is that these dark objects should propagate at a subluminal velocity. And so this is one of the key differences. The simplest type of dark object that we can have is a topological domain wall. And the simplest model which admits one of these objects consists of a single real scalar field phi, which is furnished with this potential in red here. So this is a quartic potential. Its highest power is phi to the fourth. And the shape of this quartic potential is shown on the bottom left here. We see that there are two energetically equivalent minima in this case, which are separated by a potential barrier in the middle. So the fact that there are two energetically equivalent minima, which are topologically distinguishable by virtue of the fact that the value of the scalar field here differs in terms of the sign, means that this quartic potential admits what is known as a non-trivial topology. For comparison, the usual simple harmonic potential only has a single unique minimum at the origin, and because it's a unique minimum, there is only a trivial topology in this case. The admission of a non-trivial topology by this quartic potential actually allows us to have a number of interesting consequences. So if this type of potential was produced at some point in the distant past, if the scalar field were to begin its life at the top of this, or close to the top of this potential barrier in the middle here, there is a 50-50 probability for the scalar field to end up in either the left-handed minimum or to end up in the right-handed minimum. We can have a situation where one part of the universe may happen to settle in the right-handed minimum, whereas another part of the universe may happen to settle in the left-handed minimum. The scalar field function has to remain a continuous function of the spatial coordinates, however. So this means that the scalar field has to cross over smoothly from the first minimum into the second here. And this non-trivial joining of these two minima or vacuous states goes by a number of different names. In some of the older literature, it's referred to as a kink solution. In the more modern literature, it's referred to as a domain wall. And essentially, the domain wall is this boundary or dividing region between our different domains or vacuous states. And we use the term domain here by analogy with the ferromagnetic domains that we're familiar with in ferromagnets from the field of condensed matter physics. So these domain walls are physical objects in the sense that they would carry and transport a certain amount of energy. The thickness and energy density stored inside the wall are determined by the two parameters which appear in the quartic potential, which is ultimately responsible for forming this wall. So if these domain walls interact non-gravitationally with ordinary matter, then we can expect to see some potentially interesting signatures. So in keeping with the theme of my talk today, I'd like to continue on with the possibility of searching for apparent variations of fundamental constants. And here we just have the same phi-squared interactions that we wrote down in the first half of the talk. So what we see in this case is that in the presence of these phi-squared interactions, the apparent values of the fermion masses and the fine structure constant alpha would both depend on the local value of the square of the scalar field phi. So what we would expect in this case is that if we have a domain wall, for example, moving to the left here, we would expect the domain wall to induce apparent transient changes of the fundamental constants at the location of our observer here as the wall passes through the observer. So initially, before the wall hits us, we'd expect to see one particular value of alpha. Then as the wall passes through us, we'd expect to see a slightly different value of alpha. And then finally, as the wall recedes away from us, we would expect to see the same value of alpha as what we saw initially. And the reason for why we expect to see the same value of alpha before and after the passage is that the change in alpha here is due to a change in an even power of the scalar fields rather than an odd power. So this type of idea to search for these transient variations in physical constants due to these passing domain walls has been realized experimentally by a number of groups and collaborations now. And so a number of types of searches using networks of clocks and cavities have been performed, and the results are well documented in a number of recent publications here. However, in these earlier works, there were a number of important effects which were overlooked, and what these effects concern are the so-called back action effects of ordinary matter onto the domain wall scalar field when we have these phi-squared interactions which were sought for in the previous searches. So if we have a non-gravitational interaction, which is a phi-squared interaction in this case, the non-gravitational interaction between a scalar field and ordinary matter is bidirectional. In other words, the scalar field can affect ordinary matter, and ordinary matter can affect the scalar field. What the previous searches for these transient signatures assumed is that the scalar field affects the ordinary matter field by the so-called forward action effect, which forms with the ordinary matter forming the detector in this case. However, the earlier searches neglected the back action effect of ordinary matter onto the scalar field here. And this the so-called back action effect can actually play a very important role in these types of experiments because the scalar fields which are sought have a low energy density, whereas the ordinary matter fields, for example, in a terrestrial environment, have a comparatively high energy density. In fact, the energy density inside Earth is about 30 orders of magnitude bigger than the energy density associated with the dark energy in our universe. So the latter scale is a scale which we can naively associate with these topological defects scalar fields. So what this basically means is that because we have a very large mismatch in the two energy density scales, this means that we cannot necessarily neglect the effects of back action, even when the phi-squared interaction is feeble. So what these back action effects do, or what they can do, is the back action can actually make the outcome of our experiment extremely sensitive to the details of the surrounding environment. So let's take a look at our phi-squared interactions that we have already written down. If we have a region of space where the ordinary matter is non-relativistic, which occurs, for example, in a terrestrial environment, we can rewrite these two terms as a simple sum over the various mass energy contributions to the overall energy density of ordinary matter. So for the electromagnetic interaction, we receive contributions from the Coulomb binding energies of the atoms and, more importantly, inside the nuclei. And in the case of the fermion interactions, we have contributions from the electron and nucleon mass energy densities in this case. So if we're performing a measurement in a region of space where there's ordinary matter, then in this case, the potential which is seen by the scalar field is not simply given by the bare potential, which is the quartic potential that we wrote down earlier, but instead, the scalar field phi here will actually experience an effective potential, which is the sum of the bare potential and the ordinary matter contribution, which arises due to our phi-squared interactions in this case. And the role of this ambient matter term can be seen as follows. If we first of all start off in a low density environment or have a sufficiently feeble interaction, then the effective potential is dominated by the bare potential term. And here we have our familiar shape that we saw before, where there are two energetically equivalent but topologically distinguishable vacuous states. And so in this case, this type of effective potential admits a non-trivial topology, which can support the production and propagation of the domain wall. On the other hand, if we go to an environment where there is a sufficiently high energy density, and also if the strength of the interaction is sufficiently strong, then the form of the effective potential changes drastically. And now we see that there's only a single unique minimum here, which only admits the trivial topology. And this latter situation for this effective potential means that we would tend to destabilize domain walls or even destroy the domain walls altogether. So what we see is that in a low density environment, the scalar field generally prefers to live close to one of these two minima at plus or minus pi naught. However, if we then go to a higher density environment, the scalar field tends to be pushed in towards a smaller value closer to the origin in this case. In other words, the amplitude of the scalar field phi here tends to be screened when we go to a density environment. So we have this very interesting situation whereby we saw previously that the apparent values of the fundamental constants are functions of the local value of the scalar field phi squared, but the local value of the scalar field phi is in turn a function of the local matter-based density here. In other words, if we simultaneously account for the effects of forward and back action together, we find that the apparent values of the fundamental constants are actually going to be functions of the local density of ordinary matter. In other words, we expect these models of scalar field domain walls with this phi to the 4 potential and phi squared interactions to exhibit what is known as an environmental dependence of the fundamental constants. And we don't have to go very far to realize the consequences or potential consequences of this environmental dependence. In fact, the environmental dependence can be quite important and significant in terrestrial experiments. So we know that inside Earth and also inside the apparatus, or apparatus components, the density of matter is quite high, whereas outside the Earth, where we transition to practically a vacuum state, we have a relatively low density of matter. So for certain combinations of interaction parameters, which turn out to be relevant for terrestrial experiments, the value of the scale field phi here can be strongly screened inside Earth and close to Earth's surface. On the other hand, as we go far away from Earth's surface, the value of the scalar field would tend towards its preferred minimum for the bare potential, which is at either plus or minus phi 0. And basically, what this means is that we have a sort of spherical bubble-like defect which is surrounding Earth. And this type of defect is a quasi-permanent fixture, which is basically glued onto the Earth, and it follows us as we orbit through the solar system. So just for comparison, this is the geometry of the planar type of defect, which is a freely propagating defect of cosmological origin, which arises if we neglect the effects of the phi squared interaction. And we see that in spite of the difference in the geometries of these two types of defects, there is nevertheless a connection between their properties. Specifically, if the thickness of this freely propagating planar defect is set by the parameter d, then the thickness of the spherical bubble-like defect on the left-hand side is going to be set by the minimum of the parameter d, or by the radius of Earth here. So in other words, no matter how large we make the size of this freely propagating domain wall, the thickness of the spherical bubble-like defect can never be significantly larger than the size of Earth, and this comes about from simple energetic considerations. Okay, so if we have these spherical bubble-like defects forming around the Earth, then we can expect there to be apparent variations of the fundamental constants with height above our dense body. This is because the apparent values of the fundamental constants are functions of the local value of phi squared in these models. So close to Earth's surface, we'd see one particular value of alpha. Then as we increase the height or the altitude, we start to see a different value of alpha. And what is very interesting is that these essentially static variations of the fundamental constants with height would be present even if there were no domain walls of cosmological origin in our universe. So in other words, we can devise experiments without necessarily having to worry about the domain wall passing through Earth on an extremely rare timescale of the order of millions or perhaps billions of years. So we can look for these spatial variations in the fundamental constants using a number of different techniques. So first of all, we can take advantage of the observation that the overall the overall masses of test bodies receive contributions from the Coulomb binding energy of the nucleus. And so there is an alpha dependence in terms of the overall test mass in this case. And what this means is that in the presence of this alpha gradient, we would expect it to be a small anomalous acceleration exerted on the test body. What we understand, however, is that different test bodies can be made up of different materials and perhaps different compositions and different isotopes. And generally speaking, the contributions of the Coulomb binding energies, the relative contributions of different binding energies in different materials is going to be different between different bodies. So if we choose two different types of bodies and materials, the test masses in this case would fall at slightly different rates towards the center of Earth in this case. So in other words, in the presence of this alpha gradient, we would expect the forces to violate the Einstein equivalence principle in this case. Okay, another idea that we can take advantage of is we can also compare clocks at different heights to measure the difference in the value of alpha. The ideal type of experiment that we can perform in this case is to have one of the clocks located close to Earth's surface, and then we can also position the second clock in space, for example, on board a satellite or spacecraft, ideally at an altitude of at least 10,000 kilometers. In practice, It's not necessary to have the height separation of more than 10,000 kilometers, because if we recall from the left-hand graph, the thickness of the spherical bulb-like defect can never be significantly larger than the size of Earth here. So by having the separation at 10,000 kilometers, this means that regardless of the value of d, we can always have the maximum possible change in alpha by positioning the two clocks in this ground to space clock comparison. Now, space-based clocks are, of course, the space-based clock missions are, of course, very difficult, challenging, and expensive. But in the meantime, it's possible to take advantage of state-of-the-art comparisons in purely ground-based experiments. Indeed, in ground-based experiments, we can still use relatively tall structures. For example, in Tokyo, there is the Tokyo Skytree Tower, which is about half a kilometer in height. And recently, the group of Professor Katari from Tokyo actually compared the frequencies of fronting clocks at the base of the tower with a point close to the top of the tower. And in this case, we can also search for these differences in alpha using this way. And this method is quite sensitive for thickness parameters d up to about a kilometer or so. Finally, we can also compare atomic and molecular spectral transitions in the laboratory where we have a dense environment, and we can compare the same lines in a distant astrophysical environment where there are low-density gas clouds. Now, distant gas clouds are low density, and they also have a large astrophysical size, and they're essentially devoid of screening if they don't have any dense objects near them. Okay, so just before we turn to the results, I'd just like to briefly discuss how these domain walls can be cosmologically produced without any additional assumptions in this particular model. If we start off in the early times of the universe, then the density of the universe for certain interaction parameters would be sufficiently large as to ensure that the form of the effective potential takes on the shape that we saw earlier when the ambient matter contribution dominates for scalar field values which are not too large. So there's a unique minimum in this case, which admits a trivial topology, and therefore we do not form any domain walls in this case. However, as the universe expands, there can come a point in time where the density of matter falls to such an extent that the ambient matter term is no longer important. And in this case, the main contribution to the effective potential seen by the scalar field is going to be from the bare potential term. And now we see that we have this effective potential with two energetically equivalent minima, which are topologically distinguishable. And so in this case, the distantly separated regions of the universe would tend to settle in the different vacua minima states from the top of the barrier with roughly a 50-50 probability, with a 50-50 probability. And at the end of the day, we expect typically about one of these domain walls to survive to the present day. Nevertheless, even if there were only one of these domain walls surviving to the present day and stretching across the universe, the fact that these domain walls are basically infinite in two spatial dimensions means that the gravitational effects would actually be quite profound. In particular, the gravitational effects of the wall on the cosmic microwave background radiation, specifically the quadrupolar temperature anisotropy spectrum, constrains the total energy content which can be stored in the wall at the level of 1 part per 100,000. In other words, these types of domain walls cannot account for the observed dark matter, and nor can they even saturate the majority of the dark matter. So here we have the limit on the fine squared interaction of this domain wall scalar field with the electromagnetic field. And here we've assumed the minimal cosmology from the previous slide, where there is a single domain wall of cosmological origin, which is assumed to be far from our experiment. And then we also assume that the wall in this case has the maximal allowable energy density in this case, which is consistent with the astrophysical and cosmological observations. So what we see in this case is that we can derive very powerful bounds by looking for these alpha variations with different heights above Earth's surface. The accelerometer-based bounds are shown in green and blue. The green bound is from the space-based accelerometer or the microscope mission, And the blue band here is from the ground-based accelerometer experiments. Then the clock comparison limits, at different heights are shown by the regions in red and yellow. So the region in red here is the ground-based clock comparison experimental limit, and the yellow region here are for the ground to space clock comparisons. So the colored regions here are very significant in that they give us a very sizable enhancement of the previous limits shown in dark gray, which come from different types of non-transient signatures, and the improvement is actually by up to 15 orders of magnitude in this case. Also, we see here these interesting lines. So we see that there's a purple line here, and there's also a brown line here. So these are the lines which correspond to regions of parameters where these domain walls can be produced cosmologically. Specifically, the purple line is when the domain wall gets produced shortly after the Big Bang nucleosynthesis epoch, which was about a few minutes after the birth of the universe. And then the brown line here is if the domain walls were produced after the cosmic microwave background radiation epoch. So this is about 400,000 years after the birth of the universe. So knowing how the limits, which we derived in the colored regions, scaled with the total energy density stored in this domain wall, we see that if we decrease the amount of energy stored in the wall, these colored regions would eventually start to touch the colored lines here. And so by knowing how the limits scale, we essentially conclude that we rule out energies stored in these walls at the level of 1 part in 10 billion of the total energy content of the universe. In other words, by looking for these effects of varying fundamental constants with varying heights, we actually get limits which are at least 5 orders of magnitude stronger than the bound which we get from considering the purely gravitational effect of the cosmological domain wall. Now, if we're feeling more adventurous, we can also entertain the possibility that the domain wall network may somehow saturate the local dark matter content, which is what was assumed in experimental searches for the transient signatures of domain walls passing through us, for example, with clock-based networks. And in keeping with the earlier literature, we'll also assume that the average passage of the walls through Earth occurs in a timescale of the order of a day, but still assuming that the walls are that adjacent walls are well separated. So in this case, we can likewise derive limits from the effect of searching for these alpha variations at different heights. So the accelerometer-based limits which we derived are shown in blue and green, and the clock comparison limits at different heights are shown in red and yellow. So what we see here is that the colored regions give a significant improvement of the previously reported limits using clock networks to search for the transient signatures of passing domain walls, which is shown by the purple lines and also by the brown line here. And also our colored regions here give up to 10 orders of magnitude improvement of the previous bound from different types of non-transient signatures, which are shown in dark gray here. I would also like to draw your attention to the observation that the previously reported limits from these network-based searches for the transient signatures of passing domain walls in the purple and brown lines here actually live in regions of parameter space where the scalar field would be expected to be strongly screened by Earth and potentially also by Earth's atmosphere or even the apparatus components. So in this case, it makes sense to question the veracity of these results, because in this case, there would be a strongly repulsive back action effect by Earth onto the incoming domain walls, and this may actually prevent the unperturbed passage of the walls through the Earth here. So in other words, the analyses which were performed perhaps may need to have used different analysis techniques. For example, what may happen is that the domain wall, instead of passing through Earth in an unperturbed fashion, may instead do the following. So the domain wall may approach the Earth, but because of the strongly repulsive back action effect by the Earth onto the wall, the nearest part of the wall may start to wrap around the Earth. And then at some point, the wall could pinch off. And whereas the rest of the wall passes, continues to pass through, the part of the wall which wraps around the Earth would form a sort of bubble here. And this bubble could in principle be either stable or it can also be metastable. This depends on, of course, the details of the interaction strength, of how strongly the wall interacts with Earth, how much kinetic energy the wall has, and also what the relative size of the wall is, what the thickness of the wall is relative to Earth size. If the bubble is metastable, what can happen is that the bubble may oscillate a number of times before collapsing to the center of Earth, and then it can radiate and release energy in the form of relativistic scalar particles. In other words, we have scalar radiation. So the main take-home message here is that the previous network-based searches for the transient signatures of passing domain walls may have assumed signatures which are qualitatively different from what they may be in reality. And just before I conclude, I'd just like to relate everything what I said in the second half of the talk to what I said earlier in the first half of the talk for dark matter. So in the second half of the talk, I talked about domain walls, whereas in the first half of the talk, I talked about oscillating dark matter fields. So both of these scalar field models have objects where there is a certain scalar field amplitude phi0 here. In the case of a domain wall, the scalar field amplitude phi0 tends to grow with the average separation between adjacent domain walls. On the other hand, in the case of an oscillating dark matter field, the scalar field amplitude phi0 grows with the constant wavelength of the dark matter field. And the crucial point is that in the clock-based experiments which have been performed so far, the scalar field amplitude is typically many orders of magnitude larger in the searches for the oscillating domain, oscillating dark matter fields than it is in searches for domain walls. And this is because the constant wavelength of the dark matter field, which was sought in these clock-based searches, is many orders of magnitude bigger than the average separation between domain walls, which were assumed in the previous searches here. Basically, we have a larger value of phi naught in the case of the oscillating dark matter field searches, and having a larger value I'm sorry, my slides seem to have gotten stuck. Let me just reshare. Oh, perfect. I'm very sorry about that. So the main take-home message. The main take-home message is that the scalar field amplitude in searches for the oscillating scalar dark matter fields is typically much larger than in searches for domain walls. And having a larger scalar field amplitude means that we can be sensitive to feebler interactions when we look for these oscillating scalar dark matter fields. In other words, we can be sensitive to larger values of the interaction parameter lambda in this case. And so we see that the clock-based searches for the oscillating variations of alpha in this case correspond to the red line here, which lies quite far away from the region of parameter space where the scalar field would be strongly screened by Earth. And in this region of parameter space, when we go far away from the gray region, the oscillating signatures actually generally start to overtake the non-oscillating signatures in the blue line over here. On the other hand, if we were to show the analogous plot in searches for domain walls, the red line would start to live in the gray region here. In that particular case, we see already here that the non-oscillating or non-transient signatures would tend to dominate of the oscillating or transient signatures in that particular case. So to summarize, I've discussed a number of models in which apparent variations in the fundamental constants can arise. So the two models which I focused on are those of ultra-low mass dark matter, which is in a scalar field form. And I've also discussed scalar field macroscopic topological defects. So we can probe these variations in the fundamental constants by using a number of relatively new ideas and approaches, which are principally based on the idea of utilizing and leveraging precision low energy experiments. One of the very powerful techniques in this regard involves atomic spectroscopy of clock-based measurements. And in certain situations, optical cavities and interferometers can also be used as relatively powerful probes. So the main take-home message is that by using existing data sets and searching for these effects of varying fundamental constants, what we've been able to already achieve is improve the limits on both these types of scalar field dark matter models and also scalar field domain walls by up to 15 orders of magnitude in both cases, compared with the previously known limits. So on that note, I would like to conclude. I would like to thank you very much for your attention, and I'm happy to answer any questions.